This video is on solid revolution. I have this yellow region right here and I want to revolve it about the line y equal to 1 and then find the volume of the solid revolution. And so this is the yellow region that I want to revolve about the line y equal to 1. And so this region right here is bounded above by the line by the function g of x equal to x plus 2, and then it's bounded below by the function f of x equal to 0.2x squared plus 2. And so the first thing what we want to do is find the points of intersection, see where these two graphs intersect, meaning we want to find this point right here and then this point right here. And so to find the points of intersection, we just set the two functions f of x and g of x equal to each other and then solve for x. And so we set the 0.2x squared plus 2 equal to x plus 2. And subtract 2 from both sides and then move the x here to the left side and we get 0.2x squared minus x, and then common factor is x, so we get x times 0.2x minus 1 equal to 0. And then set x equal to 0 and set 0.2x minus 1 equal to 0, and then right here solve for x, then we get x to be 5. So when x is 0, y is 2. And so this point of intersection right here is 0, 2. When x is 5, y is 7. And so this point right here, point of intersection, is 5, 7. And now let's revolve this region right here around about the line y equal to 1, and this is what they would look like. And so for the solid of revolution generated by the line g of x equal to x plus 2 will be the outer solid. And then the solid of revolution generated by the function f of x equal to 0.2x squared plus 2 will be the inner solid of revolution. And what we want is the solid of revolution between the outer solid and the inner solid. And so what we can do is find the volume of the outer solid and then find the volume of the inner solid and then subtract. So this is the outer solid. So we want the volume of this outer solid, and then here's the inner solid. So this is the outer solid, and then this is the inner solid. And now let's find the volume of the outer solid. So the first thing I'm going to do is I'm going to divide the interval from 0 to 5 into n number of sub-intervals. So the first value here, let's call it x of 0, which is 0, and then we get x of 1, x of 2, x of 3, x of 4, and then eventually we'll get to the ith interval, and right here, this will be x of I minus 1, and this is x of I, and then all the way up to 5, and then right here we get x of n, which is 5. And so let's say that n is 5, meaning we want 5 sub-intervals, and then the length of each sub-interval will be 1, since we have 5 minus 0 dividing by 5 is 1. And so the thickness of this disk will be 1. But if n is 50, meaning we want to have 50 sub-intervals, then the length of each sub-interval will be 5 over 50, which is 0.1. And so the thickness of this disk will also be 0.1. And so in general, the thickness of each disk will be 5 over n. Let's denote the thickness of each slice as delta x. And so to find the volume of this outer solid of revolution, and just like before, what we would do is to divide the solid of revolution into many slices or many disks. And this is one of the disks. And so this is the ith disk, and it comes from this subinterval right here. And so right here, this would be x sub I minus 1, and this would be x sub I. And so x sub I is about right here. And so g of x sub I would be the distance from the x-axis up to the graph. And so g of x sub I would be from here, from the x-axis up to right here. And so notice that g of x sub I is not the radius of this ith disk. And so to get the radius of the ith disk, we need to do g of x sub I minus 1. And so it's the distance from here to the from here to the x-axis, and then minus this part, which is 1. So the radius of the ith disk is g of x sub I minus 1. But g of x is x plus 2, and so we get x sub I plus 2 minus 1, which is x sub I plus 1. And so the volume of this ith disk would be pi times the square of the radius times the height. And so we would get pi times x sub I plus 1 squared, and then times the height, which is the thickness of the disk, which is delta x. Now, if we slice this outer solid of revolution into n number of slices, or n disks, then the volumes of n slices would look like this. This would be volume of slice number 1, volume of slice number 2, and then volume of the nth slice. Then using summation notation, then we would have I running from 1 to n with the expression pi times x sub I plus 1 squared times delta x. Once again, delta x, that's the thickness of the ith slice, and then the radius of the ith slice is x sub I plus 1. And then simplify x sub I plus 1 squared, we get x sub I squared plus 2x sub I plus 1. And so this is the volumes of n slices. And so the volume of this outer solid of revolution is approximately this sum right here. And if we want the exact volume of the solid of revolution here, then we need to divide the solid into an infinite number of slices, meaning let n run to infinity. And so when n approaches infinity, then we would write it like this. The limit of this sum right here is n approaches infinity. And when this limit exists, then we would define it as this definite integral from 0 to 5. 0 to 5. And then here we have pi, and then x squared plus 2x plus 1, and then dx. And then to evaluate this definite integral, the integral for x squared is x to the third over 3. The integral for 2x is x squared, and the integral for 1 is just x. And evaluating from 0 to 5, when x is 5, we get 125 over 3. When x is 5, we get 25, and then 5. And when x is 0, we just get 0. And then simplify everything, we get 215 over 3 pi's times pi. And so the volume of this outer solid of revolution is 215 over 3 times pi. And now let's go find the volume of the inner solid of revolution. And this is the inner solid of revolution. And again, to find the volume, we would divide the this solid into many slices, and this is one of the slices. So let's call this the ith slice, and it comes from this ith subinterval right here. And so right here, this would be x of I minus 1, and this would be x of I. And so x of I is right here on the x-axis. And so f of x of y would be the distance from the x-axis up to the graph. But notice that f of x of y is not the radius of this ith disk. And so to get the radius, we need to do f of x of y minus 1. So f of x of y is the distance from x-axis up to here, and then we need to subtract 1 to get the radius of the ith disk. And so the radius will be f of x of y minus 1, but f of x is 0.2x squared plus 2, so we get 0.2x of I squared plus 2 minus 1, which is 0.2x of I squared plus 1. And so the volume of this ith disk will be pi times the radius squared times the height, and so we get pi times 0.2x of I squared plus 1 squared times delta x. And this will be the volume of the ith disk for this inner solid of revolution. And if we divide this solid of revolution here into n slices, then the volumes of n slices would look like this. This would be volume of slice number 1, number 2, and the nth slice. And then using summation notation, we will get I running from 1 to n. And then 0 pi times 0.2x of I squared plus 1 squared. And then simplify this part right here, we get 0.04 x of I to the 4th plus 0.4 x of I squared plus 1. And so this is the volumes of n slices. And so the volume of the solid of revolution is approximately this sum right here. And if we want the exact volume for the solid of revolution, then we need to divide it into an infinite number of slices, meaning allow n to run to infinity. Then we would get an expression like this. The limit of this sum is n approaching infinity. And when this limit exists, then we define it as the definite integral from 0 to 5. 0 to 5. And then this will be 0.04x to the 4th, 0.4x squared, and then plus 1, and then dx. The integral for x to the 4th is x to the 5th over 5. Integral for x squared is x to the 3rd over 3. Integral for x for 1 is x. And then evaluating from 0 to 5. So when x is 5, we get 25. And then here we get 50 over 3. And then here we get 5. And when x is 0, we just get 0. And then simplify everything. Then we get 140 over 3 times pi. So this is the volume of the inner solid of revolution, which is this. And so the volume of the solid revolution that we're after is the volume between the solid revolution between the inner and the outer solids. And so this is the volume of the outer solid of revolution, and then this is the volume of the inner solid of revolution. And so we just subtract and we get 25 pi. And this is the volume of the solid between the outer and the inner solids. And that's the end of the video.